Okay, so welcome. It's fun to be here. It's been fun actually to look at some of the expos, things happening in the Expo Center. I noticed that there was some, that Intel was talking about Internet of Things and using drones. And you hear me?
Droning your way.
Oh, you are? This needs to go somewhere else?
Let's go right up here.
Okay. Okay, great. Oops. Is that good? Okay. Sorry, I'll start again. So good afternoon, thanks for coming. It's great to see some of the things in the Expo Center. There was Oculus Rift there, I think you noticed, and the 3D visors. And in GE, a lot of that work for augmented reality and overlay isn't in the future. It's real and it's here and now for us because we don't have to make consumers adopt Google Glasses. We already have entire workforces that are wearing safety goggles at all times and in many cases hard hats as well, where we can store extra memory and batteries. So we have a lot of work going on that way and a lot of reasons also to keep things heads up and hands free. Right? Hands being busy, covered with grease, in leather gloves, etc. Right? A lot of reasons to go with those sorts of form factors. So it's one of the places with Internet of Things in general and the user experience around it where a lot of the industrial commercial applications are leading. However, as GE, we play across the entire spectrum. We have appliances, make appliances, all the way down to light bulbs. So we're in your home and then your transportation system, aviation, your power generation, right? We play in a lot of different places. I have some good news, though. A lot of the GE presentations can be very, very heavy on data points with huge convoluted graphics. I only have one slide like that today. For those of you who ate a big lunch, this is very good news. I only have one slide like that today, and I'll probably make more fun of it than use of it. So. Yeah, those of you who everyone likes to make fun of economists, right? Especially macroeconomists. So we'll do that. Most of it will be pretty easy on the data, but conceptually, I'd like you to take a couple journeys with me today, which are going to be important and I think will tie to a lot of the work you're trying to do and all of us moving together collaboratively to make self-optimizing large-scale Internet of Things a reality. There are a lot of challenges. We have some good foundational pieces, and we have a lot of missing pieces as well. So first of all, there you go. That's not a very complex graphic and a pretty easy data point. Just in terms of number of things, we have a lot more number of things in the commercial and industrial space than we do in the consumer. That's probably not as significant when you're trying to optimize as what your optimization target is, right? A house is a pretty finite space with a pretty finite number of dimensions across which to optimize. A global logistics system, a global transportation network, or an aviation network, or an energy grid, okay, has a lot more pieces, has a lot more complexity to it. But beyond these numbers, I mean, I think all of us right now at this stage are more interested in these numbers. What's the opportunity size? And so this is the slide I warned you about where we get to make fun of macroeconomists a little bit, right? $70 trillion, that's a nice number to start with at the top, right? And as we trickle down, when we look at what at GE we're calling the industrial internet, it's a huge, huge opportunity. So when we start to talk about 15 trillion, $30 trillion of benefit we can get from connecting and optimizing these huge ecosystems in ways that we couldn't imagine before, these numbers are a little mind-boggling. So then we backed out and we have some numbers the other extreme. If you've seen any of our Minds and Machines presentations, et cetera, where we talk about the power of one, and we talk about just a 1% improvement, or just 1 mile per hour, faster average locomotive speed. And these kinds of improvements in the industries that we serve still come to hundreds and hundreds of billions of dollars. Very, very big opportunities, even if you just make a small improvement, even if you don't, we talk about wiring and connecting everything. Even if you don't wire and connect everything, even if you're careful about what you're optimizing on, and start with something that's very feasible, the opportunities are absolutely enormous. And so now, I should introduce myself. Hi, my name is Julian. I'm the guy who goes from the $30 trillion slide to Mr. Potato Head. I'm that guy. So Mr. Potato Head is actually going to help us talk about what's there and what's missing, just because it actually it makes the point pretty starkly. So one of the things that's there is lots of big data technology, right? That's great. We can be less discriminating about what we store, less discriminating about what we process than we ever have before, right? We can just take exabytes of data in, exabytes of data out, no problem. So big data, we have the technology there. And then add that with that big compute. So I want to ask a very complex question. I want to get it in a very short period of time. I don't need to discriminate anymore. If I have 100 algorithms and they all are good about optimizing some part of the problem space, great, ensemble. I just throw them all together and I run them all, right? And we couldn't do that before. It wasn't feasible. It wasn't cost effective. So for both of these pieces of technology, right, big data, well, I should say families of technology, big data technologies and big compute technologies, it wasn't just a matter of a few technologies coming together. It was fundamentally getting to a point where we could do things exponentially faster, cheaper, bigger. Right? Ask questions we'd never asked before that wouldn't be feasible economically before or feasible technically before. So now, Mr. Potato Head makes a good point for us that we're missing some very critical pieces, right? Which is why I used Mr. Potato Head. There actually was a reason. So I want us to all go on a journey to figure out what some of those pieces are, because that's where the opportunities are. There are a lot of players in the big data and big compute space, and yes, we're still doing investment and pushing frontiers on enhanced security, et cetera, right? There is additional work to be done there, but there are a lot of players in the space. The new ones that we're going to explore, there aren't a lot of players, and we all need to collaborate. There's work for all of us to do around those spaces, or around what's missing. So here we go, time machine. If we can all hop in a time machine and we'll go 6 months into the future. Okay, so we're going to have GE Software Incubator-a-thon in 6 months, and we're going to go to one day before that. So let's say April 20th, 2015. I have to make sure I don't say the wrong year just by habit, right? 2015. So how many of you have a birthday between now and April? This is after lunch. We've got to get some activity going. How many of you have a birthday between now and April 20th, 2015? Okay, here we go. Happy birthday to you. Okay, and happy Halloween, happy Thanksgiving. What do we got? Happy Hanukkah, happy Kwanzaa, Merry Christmas, Happy New Year, happy Valentine's Day, happy Chinese New Year. I know I'm missing a whole lot. Okay, but basically we're all there, right? We're 6 months in the future now. And this incubator-a-thon, here's what we're going to do. We're going to look for the optimal team. We have the ideas, we have the challenges. Okay, we're just going to look for the optimal team. So all of you are coming to this incubator-a-thon, and we're looking for a good mix in that team, right? We're looking for, of course, uber geeks. You better have somebody who really understands, advanced optimization and decision support. You need a schmooze machine, someone who can do business development, strategic partnerships. You need a champion cat herder, somebody who knows how to run a business, do product management, right? So we're looking for this kind of mix of team. And each one of you would have a different way of approaching that problem. So here's what we've done before the meeting. We've taken all of your CVs, all of your resumes, and we processed them. That's a good unstructured data processing. Then we've actually cross-referenced a lot of things to take the reality in your resumes away from the creative writing. Okay, one of you in here, I won't name names. One of you actually has had your resume optioned for a Hollywood movie. Okay, so somewhere along there, we got to find that. So we have a basic data set about you, but we actually go much further. We ask each one of you, we actually give you a data science team, and we tell you what is going to be your algorithm for building this optimal team. And then we go acquire any of that data. And you all have to sign, privacy is not an issue, okay? We're going to get whichever physical data points we can on you. So we'll have very big data, right? And we'll have a very wide variety of algorithms. Each one of you, what is the way you would construct this team to win and get investment and customers in this incubator-a-thon? Okay, so we do that. We've done that. We have data. Some of you, in looking, you've been analyzing the way people organize their closets, their driving patterns. You have all sorts of data, almost any of the physical data we could have on any one of you, and we have a whole lot of algorithms. It's the day before this event, and someone from my data science team comes in and says, let's call off the event. We don't need the event. I say, what are you talking about? Why don't we need the event? Well, we have a whole bunch of very smart people that worked with great data science teams, and we have incredible algorithms, right? We don't need the event. We're just going to take all those algorithms. We're going to give each one of them a vote. They'll tell us what that optimal team is, and then we're just going to have them win. And that's what we try to do a lot of times in big operational environments. But if you think about Mr. Potato Head and what Mr. Potato Head was missing, we don't have the most key pieces of data, right? We could do that. We could create an ensemble. We could have this vote. But I promise you, that team that was selected wouldn't be a functional team. Wouldn't be what is the chance that that team will be a team that would make it through the high stress of building a successful startup if we funded it? Yeah, very, very close to zero. Because the most important data that we need at that point is how you would all interact, and how you deal under stress, and how compatible your personalities are. And all this stuff we're only going to get by bringing you together. So I tell the data scientists, get out of here, right? Get out of here. We are going to hold this event. And then we hold this event, and all of you are there. And you've used your algorithms, and you've specified who you want to be on your team, right? And so we mix and match. It's very difficult. No one gets their complete wish list. Each one of you is matched with at least one person you wanted to be with. And we give you challenges. We create pressure. We give you hard challenges to solve. And you're working on those together. What are you going to find? Right? In many cases, that person that you selected you really wanted to be on, you're like, they're a jerk. I couldn't work a day with them. And other people, you're like, wow, man, their data didn't look that good. But this person's a champion. If we had a startup together, no one could stop us, right? And you're going to do that and collect that, okay? And so now we're starting to get the meaningful relationships about the interrelations and connections. It wasn't in there in any of our underlying data, right? It's that interaction, it's that relational data that we get. Now, but each one of us is collecting this, and there's something that's still inefficient. Each one of us is doing this in team if we're in teams of 5, okay? But if you're a team of 5 over there, okay, in the back on the left, you don't know what's being found here about how someone deals with stress, pressure, how collaborative they are, et cetera. That's fundamentally inefficient, right? And so one of the big areas that's missing, right, is big context. We got to see what this Internet of Things really looks like, how everything interacts with each other. And so some of the pieces have been coming together under here, right? So let's ask, I mean, what do you think are some of these underlying technologies that help us along here that we've been tracking? Any ideas? So we've had a few players that have said an Internet of Things is well described by a graph-based database, right, by a triple store. Okay, maybe that's a foundational piece. But is that enough, right? Does that really solve the problem we talked about where we don't each have an idea about what the other one is doing? Maybe. We have one reference big context that we're all constructing collaboratively. Maybe that gives us a place, right, to start inquiring and at least say, nothing's going to be hidden. But the other problem is around the way that we create that big context. It's arduous, right? It's a very slow process. Are there any ways that we can speed that? And then where did we invest our work before? Well, before this work, this incubator-a-thon, we'd all worked with data science teams to create those algorithms. We were investing our effort in the algorithms. Okay. But the algorithms were blind to the most important thing, which was all the interconnections. Now we have the interconnections. Shouldn't we shift our focus from creating custom, bespoke algorithms to actually logic that generates the algorithms from the big context just in time, right? These are a whole slew of technologies we don't have, right? So we do a lot of work optimizing very large-scale, complex Internet of Things, hospitals, hospital networks, factories and supply chains, rail networks, energy grid, power grids, right? Global aviation operations. We also generate models versus building them because we know then, right, that we don't have to manually update each model, that we can learn faster, that we can improve, right? If we want to get to self-optimizing, if we want to get to those fast feedback loops. So we do that, but let me just tell you a scenario, and then we can start to get a real feel for where we are and where we need to go. We buy a lot of companies that have compatible products, a lot of manufacturing companies. We do a lot of manufacturing. So let's say we buy a new company. They have 15 factories. They have great products, but these factories are functioning very inefficiently. They're always reactive. They always have late orders. They have lots of partially worked work in progress, lots of partially worked material sitting around on the floor. They're always having to do emergency rush orders, so they have low visibility and they're very reactive. And I could go to power generation being this way, and I could go to oil extraction being this way, and hospitals running this way. Actually, let's ask a question. Okay, so in the last year, how many of you have been delayed during air travel? Can you raise your hands? Okay, right? How many of you think that oil and gas prices are too high, or your energy bill's too high in your house? How many of you have waited in a doctor's office, right? Or waited in a hospital to be discharged? These things happen all the time to us. So the industrial and commercial Internet of Things, as we start to optimize it, has real impact on us that we actually care about very much, right? In this case, with these factories, you might say, that's a long ways away from me, a manufacturing thing, but it's a closed environment. So let's talk about that. What would be fantastic is to go in that factory with a SWAT team and a bunch of technology, and in one day, in 8-hour shift, let's back up. These factories often operate 24 hours a day. So let's not say a day, because that's actually 3 shifts. In one 8-hour shift, to go from reactive with low visibility to proactive with phenomenal visibility in a factory. So let's imagine what that looks like, right? And the technologies that come to bear. So, I was talking about some of the technologies we're using. We're using the heads-up display in the visors. We're also using drones. We're already using them in factories. We're already using them on wind farms to do inspections. We have a lot of hard to get to places, and a lot of places where it's difficult or dangerous to place sensors. We need to use advanced image analysis, et cetera. So for us, that's all real. So imagine you have experts, you have a bunch of drones you can deploy, they get a feel for what's there in the factory, you're looking at all the underlying systems, you're seeing what's there, you're collecting that data. Now, we have a lot of factories, we have similar factories. So let's say we have a referenced big context graph, right? So that's a good asset. But still, it's going to take a lot of time and a lot of work and a lot of expense to place sensors across this entire factory, et cetera. So we want to know what is the least intrusive, shortest time to insight that we can get. What is the fastest way, and what are the most valuable things to get? So we don't just go get 100,000 data points, okay, on this Internet of Things. We get the things that are really going to help us turn the corner for this factory. So if any of you are working in the Internet of Things space, what I just described wouldn't take 8 hours, right, currently. It wouldn't take 8 hours for us to go in and take a very reactive, inefficient operating environment and make it turn the corner to be towards a space where we could get it to be self-optimizing. To start to get proactive and to start to have visibility. And then on top of that, we add constant learning, constant optimizing, which is once again back to the shared grid. It's not efficient for one solution, spot solution over here to be optimizing its own context. We all have to be optimizing one shared context. Make sense? Silence. So I wanted to open it up actually for questions. And actually, I walked around a little bit beforehand, and I know some of the IoT challenges some of us are working on. Some around consumer content, entertainment, relating an IoT to a social graph, preferences, energy generation. So are there any questions or thoughts? Yes, please.
So a counterexample, if you would, you do all this analysis on the power grid.
Yeah.
And every once in a while you find the power grid just goes crazy, random failure.
Yes.
And you scratch your head and some operator, some low-level operator says, it's solar.
Yeah.
How does big data give you insight into something that the model has not accounted for? Another example, turbines in aircraft engines.
Yeah.
Every once in a while, blade breaks, hopefully it's contained.
Yeah.
Can you predict that? I mean, I know there are failure models, but
Yeah.
can you predict the day that particular engine is going to have a blade failure? I mean,
So with much better accuracy when we have the big context. So right now, a lot of the big data applications are around physics-based or chemistry-based problems, right? It's one right answer based on hard science. And so you look for a physics-based, early signs of a physics-based failure signature, right? And we can sometimes detect that a long ways out. So we say there's some preventive maintenance that needs to be done.
well, they do that for aircraft engines.
That's right.
Ultrasound the blades or whatever they do.
That's right.
X-ray them.
We do that.
But they have to take the engine apart to do that.
Yeah, so that's one of the things is there's a lot of technologies that need to be less intrusive. Technologies where we can do that without disassembly, where we can do that in the field, or we can do that continuously. No, but a lot of times is what bites us is we don't understand the entire operational environment, okay? It depends where you're flying the aircraft. Are you taking off a lot in the desert, right? Is it sandy, hot, dry? What altitude you're operating it at, how fast you're climbing. All these this operational context, right now, that's when I'm talking about the data that doesn't exist. That's a lot of the data that doesn't exist right now. So we'll have this absolute oodles of machine data. It's like us having all of the data on each one of us before this event, right? And we could run algorithms on those data, but how good is that going to be for predicting how we'd all operate together? It's the same thing. When we don't have a shared big context of how everything in this entire grid works or everything in this entire network works, right? It's only so good. And so it's critical that we build this. Yeah. Thank you. Those are good examples. Yeah, thank you. Any other? Yep.
So how do you use big context in the example question which we had actually?
Yes.
The planes,
So when we're doing just physics-based, a physics-based algorithm, looking for certain anomalies, right, or certain physics-based failure signature, that's more of a big data problem. But our problem has been that we don't see the difference right now between that happening because of how an engine is being serviced and how an engine is being operated. Okay? Without big context, we don't see that. If we don't know the operating conditions, if we don't know the maintenance conditions and the protocols and everything that happens about that, we can give you early warning that it's going to happen, but wouldn't it be a lot better to get all the way back to root cause? That's what we miss, right? We aren't even collecting the data on it. Or we'll have the data in completely siloed systems. So we have a maintenance system over here, but there's no connection at all between the maintenance systems and the operational systems, at all. Right? Yeah. Any other questions?
I agree with a lot of you. I agree with a lot of what you put together, and a large part of
And especially my use of Mr. Potato Head, right?
well, the big context. From what I've noticed, right, and not just now, we were doing data mining 15 years back.
Yes.
And the funny thing is, right, it's not about collecting everything. It's about figuring out what are the right things to map into. Because otherwise, if you're collecting too much, you'll have a hard time sifting through it.
That's it.
And the whole big data trend that I'm seeing for the last couple of years, it disillusions me a little bit because there's this whole movement for every company to go out and do a whole bunch of stuff on Hadoop where you're just throwing machines behind it, but you're not thinking what's the right context.
Yes.
What's the right way to do big data?
Yep.
And you have all these thousands of engineers being trained to be on Hadoop like in a month. It becomes pointless if you don't have the right context and the right architecture, the right design
Absolutely.
behind what you're trying to achieve.
Absolutely. Yeah, but we have that mix, right? We have a lot of data scientists who are looking for physics-based failure signatures or looking for, things about progression of disease. Okay, and those are great big data problems. The problem is then we come over to wanting to optimize an entire large-scale Internet of Things, and there isn't data to be had first, right? So yes, we have to be so careful, and I agree. I mean, from what we've found so far, you don't have to go bury yourself in data. You just need to start building very, very good context, right? That's shared, that's visible, that's not locked away. So initially, a lot of the work was, you'd want to do this, so you'd create a simulation model that mimicked your complex operational environment, right? And you'd be able to run certain types of simulations against that for how to best discharge patients from a hospital, et cetera, right? To help you do planning and help you strategize how to run this, or even run those in real time when something goes wrong. So you have an airport that's closing, it's going to close because of a weather system. You need to run all these huge what-ifs to see how you could possibly reroute all the aircraft, make it work for passengers, make it work for crew, make it work for equipment, everything, right? Very, very big puzzles, okay? So we've done a lot of those, but there's so much content. What's frustrating, without us going the big context approach, is that you'll do that, and then you'll have all of that context locked away, and it's only useful for one purpose. That's ridiculous, right? How are we ever going to move fast and optimize really huge scale internets of things if we do that, if we have it sequestered here and locked away there, right? We've got to put all that context out there where you can have contributors and consumers that don't know about each other, but can all benefit, right, to get that quantum leap that we're talking about. Yeah? Yes?
Just to throw something into the mix here and try and create trouble.
Perfect.
It's not just big context. I think also, and a few of us have been grappling with this, it's appropriate context.
Absolutely.
And unfortunately, very often the best insights come from non-technical people.
Yes.
They have the expertise. They have, who knows? They just see it. How do we, now where we have all this data, how do we create an environment where we can start to bring that kind of non-technical but really appropriate expertise into our appropriate context?
Yes.
And we're looking at, we need a meta data level. We need to decouple from all of the bits and pieces that we're doing, and the focus of typical engineering focus, we like to check all the boxes.
Yes.
So are you guys working on anything that may be a tool in the future to help bring in, the 99% that actually have the answers for our big data?
Yes, for us it's very important to get the human experts. So even in the example I gave about the desired state, it was a SWAT team of human experts going in with the right technology to help them. That's absolutely critical. One of the things about, the other thing about a graph as one of the foundational pieces for describing an Internet of Things, a triple store, a graph database, is that it's self-describing, right? So rather than taking all the time to design a relational database and then having it locked away there and having to have specialized tools to decipher and construct what that looks like in the real world, a graph can describe an Internet of Things in a way that's pretty comprehensible. So a human expert can look at it and say, yeah, actually that relationship is true, but only under these conditions, right? And add those kind of devilish details that are absolutely critical.
Yeah, we're calling that adding roll to the links.
Yes.
The arrows don't quite encompass. Anyway, sorry, don't mean to derail it, but exactly.
That's not derailing. That's core to all of this.
It's almost good enough that our all in the graph database fall a little bit short.
Yes. No, that's true. I didn't.
Yeah,
what I'm saying is we don't have it. We don't have it yet. We have a few pieces that are just giving us little hints to the directions we can go. But even a triple store, once it starts to grow and you have different functions and domains add to that triple store, right? They add information that other functions and domains don't want to see, and so it starts to grow and it starts to bloat. And pretty soon, what to one function, what to the person who's just worried about scheduling is metadata, right? They just want to know about people certified to do this job in this place at this time, right? There's things they care about and connections, and then these pieces of equipment that they work with, right? But if they see everything else about compliance, right, or about energy management, okay, that's also got to be in this big context, it's too much. So some of it is how can we filter and tailor views into that graph? How can we give better and more fluid user experience for people to navigate that graph and to give feedback to help improve it collaboratively? Yeah, that's core. Yeah, it's great.
I joined a little late, so sorry. I don't know what you talked about for 10 minutes.
Okay.
But this is one of the fundamental problems of IoT, right?
Yes.
There is a data overload just from sheer numbers in the future.
Yes.
But decision making relies often on synthesis.
Yes.
So that's a trade-off I think we as an industry need to strive towards, because just showing data is useless. It's not information.
No.
And the information is not useful if it is not tied to the role, responsibility, or the context of the
Yes.
person or the machine.
Yep.
I'm just wondering, when you say self-optimizing,
Yes.
there is micro-optimization, right, which is maybe just that hospital.
Yep.
Or it could be a macro-optimization, which is a hospital, which is a group of hospitals, and they're all interconnected, different services. Is GE working on these, almost a hierarchy of analysis,
Yes.
recommendations?
Yes. Yeah. So for us, yeah, we have to do a lot of low-level optimization. But once it gets back beyond optimizing the way a machine is working, right, or consuming power or whatever we're optimizing against, and we start to get out of the one right answer based on physics to the fuzzy spaces, right? That's where actually we run away from simplicity, right? With ensemble models, we say, it defies Occam's razor. It's actually, if you had 10,000 algorithms that were all good, you get a better answer by combining all 10,000 of them. If you had 100,000, even better, right? So you run right into the arms of complexity, right? Okay, for a certain class of problems. So there's that difference. We work all the way from the one right answer based on hard science, absolutely, and we're tremendously good at that, right? Then up to the fuzzy operational problems. Now at the operational level, the thing that also gets dangerous is the curse of optimizing locally and sub-optimizing globally. And that rears its ugly head immediately. The minute you get to a problem where it's what your competitors are doing and the way markets are operating and supply and demand and all the crazy unpredictable things we as humans do, right? We make everything hard from an optimization point of view, right? Yeah, then it's another beast. And so then we're worried. So it's almost like you want to make a huge leap from very discrete at that point to taking everything into account, if you can afford to, right? Everything you can into account that'll help you make a better decision. And like I talked about the recovery scenario for airlines, okay? I'm sure you can imagine the number of dimensions there are there. I talked about you have to get the planes repositioned, you got to get the passengers the right way, some way, right? The crew, you still have to worry about maintenance schedules, you still have to work that in. You need to worry about hotel rates, right? And so to try to find an optimal solution just based on cost, you're looking at hundreds and hundreds of dimensions. Very big problem space. Now in operational context for a large IoT, you're trying to optimize this. You might not have to be 20 milliseconds or even in tens of seconds to have a response. In many cases, if I want to know what's my my best way to operate this hospital for the next shift, or this factory for the next shift, or this airline, now for the next 10 minutes, you can get answers in a minute or so. But it's absolutely, when you have the models and when you have the context, it's a huge amount of compute. And it's a large number of dimensions. The other thing, I don't think it's named yet, it goes a little bit beyond this notion of optimizing locally, sub-optimizing globally. It's that often when you have local optimizations, they go to war. And then what you find in your operational context is that you're almost more dysfunctional than you were before when you were just winging it. Because now you have two prescriptive systems telling you things to do that are contradictory for very good reasons. So I'll give you an example from healthcare. Let's say we have a patient discharge algorithm that's not just going through the floors or based on nurse availability or alphabetical order or all the ways where we know we're getting out of the hospital today. 8 a.m., noon, 4 p.m., 8 p.m., we finally get discharged, right? In this way, there's some smarts behind it to say, well, actually, we're looking at who is moving out of emergency room and ICU, okay? And those, we actually now, based on healthcare regulations, we're going to get penalized if we have people sitting around in ER or ICU inappropriately, or if we have people that shouldn't be in ER and they're in ER, right? So we need to move them to another part of the hospital. Well, shouldn't we be looking at patient discharge and say, this person needs this kind of medical treatment, they need to be in this ward, that's the bed we need free right now, right? So we can do a whole system, we have these solutions, to do discharge that way. Now, around healthcare reform, there's also readmission. Okay, if they let you out of the hospital and you're back in less than 30 days, no reimbursement, right? So there's readmission penalty. Both of these have financial penalties, by the way. So they're high priorities, right? It's not just, we love you and we care about your health. It's not just your health now, okay? It's also the bottom line for the hospital. So we'd have readmission, and readmission might say, actually, no, yeah, you want to clear that bed, but that person, we can't just readmit like that. You need to do 2 tests on them, okay? And we have to have these lab techs come and administer these tests. And you do those 2 tests, and if they turn out this way, let them go. If they don't, have them stay. But one system is saying, get that person out of here immediately, their first priority, and the other one is saying, no, you can't get them out of here for at least an hour and a half, right? Well, that's crazy. Why would we want that? What we want is we want big context. We want context that describes all of that, right? So that we can make a balanced decision, and we don't get in this situation where a human's caught in the middle between 2 systems that are telling them, absolutely, this is the thing to do, right? Does that make sense? Okay. Any other questions? That's cool. I'm glad we got time for questions. Actually, I didn't start this for the timer. How are we doing time-wise? Okay, we're okay. We're great. Okay, fantastic. So any other examples or questions? Domains? What kind of large-scale self-optimizing IoTs are some of you working on? Volunteers? I knew someone was working on energy grids, but he left before I could put him on the spot. Were there any other technologies? We talked about a few technologies that could help with this, right? Help put this together. There are technologies around fast acquisition of data, low intrusion or non-intrusive sensing, so we can map a big IoT very, very quickly. We need inference engines to tell us what data to go after initially. We need engines that help us keep things up to date, right? So we also need, because these are very, very dynamic, once again, not one right answer based on physics, but very dynamic systems. A graph-based system is a potential candidate for a good description of this, or one approach. What are there other technologies or things that you guys are thinking about sort of in the mix of this vast opportunity space? Or is that too hard to ask after lunch? No, come on. I figure, you came here, there has to be an interest in self-optimizing large-scale internets of things, right? So yes?
Are there any resources that you could rattle off that you got assigned or interested in what applications that are currently being researched and stuff?
Yeah, absolutely. So a a lot of what we're doing in this space goes under industrial internet. So you almost search for industrial internet, and you're going to find a lot of things about the opportunity size, the industries, a lot of examples of different places. You can always pop me a note too, and I'll put up that slide. You can also send me an email, and I can send you a bunch of links. You know, this is so big, we aren't going to do it alone. So we have a lot of partnerships, Intel, Cisco, you know, on the compute side, Amazon, big investment in Pivotal. So it's one of these things where, you know, yeah, I sort of put it there. We're hiring. We actually have a booth over here. We're partnering. We're investing. We're incubating. It's going to take all of the above. So industrial internet is one place you can look to see a lot of the industrial applications. There's also a lot going around you know, user experience around some of this. How are you going to make all this complexity understandable once you get back, or help somebody make a decision? And so some of that is actually the GE UX Center of Excellence. If you look for some of their stuff too, you'll see some really good examples.
Can you discuss the business model where the recurring revenue would come from in doing this?
Yeah. So what everyone dreams of, including GE in this space, is as you instrument everything and turn these, you know, very reactive systems into very proactive, self-optimizing systems, that you get performance-based pay. Actually, in the company, everyone's very open about it. That would be optimal. And the recurring revenue, yes, you could say here's the baseline, and actually we're going to continue to you know, put more sensors and map a bigger and bigger context and ask more and more complex questions and help you optimize more and more, right? But even without that, with, you know, traditional licensing, et cetera, yeah, there's a lot, you know, on the hardware side, it can be a little harder, right? You say, I place a sensor's a commodity thing, I place it and there's one-time revenue. But there's a lot there on the, you know, if you can sort of have sensing as a service, right? And some of the stuff too that's compute intensive. So sometimes our option for having, you know, one sensor, which is a camera, and being able to sense, you know, then just add more and more and more algorithms in the background and sense all sorts of things, operator movements, operator activities, you know, material flow, task sequence, process, protocols, loads and loads of things you can do with, you know, then the algorithmic intensity. Then you get yourself actually also in the recurring space, right? Because then that compute and the algorithms are as a service, and you're continuing to enhance the algorithms. So I think the big thing is, you know, of course, staying away from, I mean, there's going to be huge business, right? Because there's so much to instrument and the one-time thing. But when you say the recurring question,
that's my concern.
Okay.
You instrument every element, and all of a sudden your growth curve comes, you know, flat or declines or.
Yeah. Well, instrument plus the algorithms behind it, right, and the compute that you do as a hosted service.
Prove that you can continually improve the business results.
Yes.
Through algorithmic improvement, but eventually physics are going to fight you on that.
Well,
You're going to improve the process as far as the physics lets you improve it.
no, but in this case, we aren't talking about one right answer based on physics. It's a long way. Yeah, and the thing is that anything can disrupt it, right? So, you know, a factory is a good thing. It's a system. You know, we try to lean out a factory, right? Lean manufacturing, right? We get this whole thing optimized. Okay, and then something happens in the market. One of your competitors closes down, or suddenly the market's ready for your product and there's a huge spike in demand. Okay, and that optimal system suddenly becomes abysmally suboptimal, and all the leaning out you did works against you, right? Now you've got, right? How can we possibly get to this huge ramp up in capacity, right? Yeah. Sure. No, but what I'm saying is that, okay, regardless of where the factory is in the world, let's say, right? The point is that if you've got something and it's an optimized system, and because in this case we aren't talking about one right answer based on physics. When we create physics-based models, right? The physics of a turbine don't change for the first 15 years of operation. They got a very good shelf life. When you're creating the model, okay, or you know, to optimize, you have algorithms to optimize a factory. Those have a shelf life of 2 days. Things are changing all the time, Oh, they do right now. I mean, so much of our large-scale world is very, very reactive. Things change every day. Everyone's always doing expediting and emergency orders and things like that. They don't have the visibility. They don't have the big context, right? Look at a hospital, right? It's every day is different. No, what I'm saying is when the world around you changes, when your market changes, when supply and demand changes, when your competitors change, right? Or unexpected things happen, then you've got to adjust. So really, when you're talking about optimizing, we talk about 3 classes of optimizing. There's one, which is an optimal plan, strategizing ahead, right? You have more time. Then continuous operational optimization under normal operating conditions. But normal operating conditions can change. You suddenly get a huge glut of orders coming in, and you've got to quadruple the capacity of this factory, okay? So normal can change too, but here's keeping things normal. And then there's recovery. And recovery is something breaks unexpectedly, something goes wrong, and you're trying to get back to normal operating procedures. And all of those, yeah, those are big problems. And these models, that's the whole point for us sharing the task of mapping and updating context, is because the context is changing all the time. If we were talking about a physics-based model or a physical model, we wouldn't have to cooperate. You go do your thing, I'll do mine, we'll be fine, right? We could afford to do that. In this case, for large-scale IoT, we can't afford to do that. We can't afford that inefficiency. Yep.
Again, my apologies if I lost the context for 10 minutes. But when I saw the title of your talk, I assumed that there are some fundamental things we as an industry are communicating, right?
Yes.
For something to be self-optimizing,
yes.
there has to be inherent, at the low-level protocol-based sharing of state and context and things like that.
Yeah, absolutely.
And when you go up, you need something where these are serving a bigger purpose, right?
That's right.
Because we can do reasonable optimization at the lower levels of network.
Yes.
But that doesn't have any business context.
That's right.
And then you can throw in big data saying, I will capture billions of things and then try to, quote unquote, optimize is the wrong word.
Yes.
It's not a mathematical optimization, right? And then they will probably do some regression, this and that, and try to correlate. For example, the hospital, one of my friends that did an analysis and said every time anesthesiologist John was dead, it was always happening nothing, right?
Yeah.
The regression model, that.
Yes.
So that was useful, but I'm not sure if that was the only reason.
Yes.
So I think there are protocols, there are the translators, because there's no one thing in IoT. Different protocols, different sensors, different price points, different intelligence, different compute.
Yep.
And is GE, I know I've read a little about your efforts, is GE taking a stance on some of these things, or well, maybe what was the context of your presentation?
Yes. No, so some of that is going to stay messy. There's nothing for us to do about it. We work across so many industries, even if we could drive standards in one industry, right? Now, we do have things that we're doing, that are cross-industry in terms of helping you with sensors. When you were doing video analysis, image analysis, it crosses industries very, very well. But let's assume, actually, that we're going to have a lot of different things collecting information about the IoT, and we're going to have a lot of different devices out there. Let's assume that to start with, right? You're right that we need to get to some point of sanity and shared understanding. That's this big context, right? If you share a graph, and it's not a novel thought, there's already big players going, actually, we're going to have a graph database that describes an Internet of Things. It's got to have a standard, a shared semantic model on top of it, so that you could have independent contributors and consumers, and it becomes a collaboration point. So that's absolutely critical, right? Is to have that shared collaboration point. There's work to be done there, just at that level. That's sort of foundational. But then there's so much work to be done after that. But if you think about that and say, okay, if at least have that as a standard, this is the way that we build and share big context, and you agree on that, or you have a few of those players that do that sort of foundational work, right? Then you say, okay, now I don't have to do point-to-point integration. All I have to know is how to update this big context, and there would be a few versions of that. And that's all I have to do if I'm in the sensor business. I don't have to drive myself crazy. I don't have to think about every use case. In fact, I don't even have to know how I'm being used. That's the best situation, right? Yes?
Given that you're dealing with big context,
Yes.
how would you validate what the solution you come up with? Because especially if it's so huge,
Well,
domain experts.
well, once again, it doesn't have to be huge. It just has to not be siloed, right? So the question, let's say you create a solution that's just one of these solutions about scheduling, or like I described, patient discharge, right? Your initial problem just looks at a finite number of dimensions. It's still operational, it's still a lot. You're probably going to look at 100 factors, okay? This is typical. You look at a lot of different dimensions. But it's still considered a very narrow solution. It's a very small piece of what the hospital does as an entire system, right? The question is, did you implement that in a way so that everything you discovered along the way, right, and everything you're updating day to day as procedures and protocols change, as staffing qualification changes, right? Everything you're updating, is that locked in your system? Or is that something that can be shared by the broader community, right? And is it a nightmare now if you have two spot solutions that go to war the way I described, that are saying contradictory things? Is it a nightmare now for you to do a one-to-one integration with those two, and now you create this bigger system? But once again, this is the test. Then you create that bigger system. Once again, is that bigger system locked? Does it have context and important things, which once again, as I was stressing at the beginning, that was some of the context, right, was that we can have huge amounts of data, but the meaningful data about the interactions between things and the relationships between them in an operational context usually doesn't exist in any database. So you're creating this new data, which is remarkably important data for optimizing this operational system, and now you're locking it away, which is a crime, right? So that's the test. Is it you're putting it in a place where it's shareable?
Can you talk a little bit about some of the new work you're doing in your laboratory?
Oh, in San Ramon? Yeah. Which?
You have an innovation center, you're working on the Phoenix platform.
That's right.
Not a whole lot has been shared on the API.
That's right. Well, okay, so last week they announced that we're finally going out. So Predix was something we were developing for our own industrial internet, for our own large-scale Internet of Things uses initially. Now we're going out. So yeah, you're right. External to GE, there hasn't been access to the tools, technologies, hardware and software, APIs, et cetera, right? That's changing. So starting, well, the announcement was at Mind is in Machines in New York about a week ago. And so that's new. So now I can talk about that and say, yes, that will change. So yeah, in San Ramon, there's a lot of aspects to what we're doing. And actually, it's San Ramon, and then we have other sites as well for GE, in India, on the East Coast, in Europe, et cetera. A lot of it's around advanced analytics. It's around sensing. It's around edge compute, right? Distributed computing and edge compute, computer vision, advanced user experience for advanced decision support. Augmented reality, so you can provide feedback in these dangerous industrial environments in an effective, safe way. The gamut of technologies we're dealing with is the only thing. Okay, out there on the expo floor, there's all these different technologies. I was pretty impressed with the range, right? There was DNA, extracting DNA, and all these kinds of things, right? Probably the only thing we aren't working with out there was one presentation where it was doing facial recognition and it could put another face there. And if you went like this, it would turn you into a zombie. Okay, we aren't doing that. I think we need to find a use case for that. We aren't doing that. But almost anything else that's represented out there, we're doing and using in a real way in San Ramon. Yeah, it's very exciting.
So I've been to San Ramon, the GE office a couple of times.
Yes.
Had some discussions. They've talked with the example of GE turbine engines and deviations a couple of times.
Yes.
You give an example of the hospital system.
Yes.
Are there some specific examples you can kind of share before we run out?
Oh yeah, I think we are out of time. I think we're 5 minutes over. But actually, yeah, let's talk. There are a lot of examples, yeah, that I can talk about.
Especially
Yeah.
the whole self-optimizing aspect.
Piece of it, yeah. Well, that's actually, that's the reason I was talking about it, because that's a lot of the stuff that still needs to happen. You know, once again, not in the context of a spot solution, but in a way where you say, regardless of which Internet of Things, which industry I deploy this to, which Internet of Things, I have standard ways to update this this shared big context, you know, to keep it in sync with the real world, okay? And then to constantly look for additional opportunities for optimization, right? To explore that and say, you know, maybe based on another reference case over here, and then inquire, right? That's when you really get to self-optimizing, where you have human experts. They're really good, they're still going to continue to be important, but if you can have them be assisted not only with decision support, but now helping them know which questions would be most valuable to ask, right? That's really critical. Okay, thank you very much. Thank you.